Okay, so the last talk of the day is Tom Sutherland from Sheffield. We'll talk about stability conditions and flat connections.
Okay, thanks very much. Thanks very much for the invitation. It's very nice to be back here in Bonn. So I want to talk about some spaces of stability conditions of some Calabi-3 triangulated categories, which are somehow associated to moduli spaces of meromorphic flat connections on a Riemann surface. We're going to call M a moduli space of meromorphic flat connections. These would be SL2C flat connections on a Riemann surface. C. So an important property of this space is that it's a hyperkähler space. So it's non-compact, but it's nevertheless hyperkähler. So there's a one-parameter family of complex structures on this space M. Yeah, so I'm being rather vague here in this introduction. So yeah, you're right. I mean, to actually have a hyperkähler space here, I need to fix some choices of residues of these connections at the poles. But yeah, I guess we'll see that a bit better later. So yeah, so you have this one-parameter family of complex structures, parameterized by a CP1. And in fact, for almost all values of zeta, this space viewed in this complex structure is actually isomorphic as a complex manifold to this original space M. But so that happens over any zeta in C star. And then there are two very special values of this parameter zeta for which, namely zeta equals 0 and zeta equals infinity, in which this moduli space somehow degenerates into something else. So here we have M0. And what it degenerates into is a sort of complex version of an integrable system. So it has a fibration over a base. So this is essentially due to Hitchin in the original holomorphic case, and then I guess various other authors generalized it to this meromorphic setting. So this is a sort of complex interval system. I mean, this base B is a space of meromorphic quadratic differentials. On this surface, Riemann surface C. Right. And this space was studied by recently by three physicists, Giotto, Moore, and Knightsky. And their motivation was to try and actually describe the hyperkähler metric on this space M by correcting this, the sort of naive semi-flat metric you have on here using some sort of instanton corrections. So, and it turns out the sort of, the useful mathematical formalism for describing these space of instanton connections is is via spaces of stability conditions on triangulated categories. So I guess more precisely what we're going to see is we're going to associate to this space M, we're going to construct a Calabi-Yau-3 triangulated category which I'll call D. And then to every point in this base V of this interval system structure, we will see how to associate a stability condition on D. And moreover, we will see even how to describe this semi-stable objects with respect to the stability condition in terms of this data of a quadratic differential. Namely, we'll see that certain what are called saddle connections, so certain special trajectories of our quadratic differential will correspond to the semi-stable objects. Okay, so this really came out of, the real motivation for this is through considering some sort of string compactifications. So this space B is some sort of moduli space for a gauge theory, which can be realized by compactifying a certain string theory on a Calabi-Yau threefold. And that's really where this category came from. And that Calabi-Yau threefold is in fact constructed as a sort of vibration over this Riemann surface C. But we're going to construct this category in a very different way by looking at trajectories of these quadratic differentials, and we're going to construct this category in a much more combinatorial way. Okay, so we should start by talking more precisely about what I mean by the quadratic differentials we want to look at. So first, I'm going to fix some notation. So I really want to consider C as at least to begin with, as just a smooth oriented surface. I'll have genus G, and I want to package the data of the poles of these quadratic differentials in what I'll call P. So this is an integer-weighted marking on C. So that's just some collection of points, Pi on C, together with some integers, Mi. Oh. Yeah.
I don't understand what's the relationship between this the middle part of the black hole and the crystal family? Or are you forgetting the crystal family and basically concentrating on the M0 now and constructing the hyperkähler metric well?
Yeah, I mean, so for, well.
You are relating, this is the relation between M0 and model specific connection. Now you are,
Yes.
model specific is balanced.
Yeah, essentially. So I guess, I mean, the relation is that you can, yeah. So the way Giotto, Moore, and Knightsky went about constructing this hyperkähler metric was to start with a sort of natural metric you have on here, which is flat along the fibers. They call that semi-flat. And then correct that by some given formula which depends on a point u in this base B. And I guess what I'm going to try and say is that, in fact, such a point can be actually interpreted as a stability condition on some derived category, which I intend to describe. So, I mean, I guess.
The modulus space of stable object will be H in fiber. Not relates to the generic point of this crystal family.
Well, I mean, so the way in which they actually construct the metric is not in a sort of direct way. They actually use this twistor formalism and construct, they construct what are Darboux coordinates for each given m zeta with respect to the symplectic structure, complex symplectic structure on m zeta. So they really are constructing something which is relevant for a generic fiber of this. But what those coordinates depend on really is this a point in this space here. Yeah.
So you are using the fact that there is a differentiable trivialization to map to M naught, and that map to B, and so the whole crystal family maps to B.
Yeah, in some sense.
Okay.
Yeah.
What's the dimension of M?
Right. So I guess I haven't really quite specified. So I mean, by meromorphic here, I really mean with some specific orders of poles, which are going to be controlled by this. So I think, well, we're pretty much far enough for me to be able to answer that. So let's say there are n of these marked points. And I'm going to impose this slightly bizarre looking condition that all these integers are at least 2. So these integers are going to specify the orders of the poles of the quadratic differentials at these marked points. And then, I guess to answer the question, as a complex manifold, the dimension of any one of these m's is then 6p minus 6 plus the sum of these mi plus, well, I'll write this as n odd, so the number of odd mi's. Okay, so we have this data, and then I want to consider some quadratic differentials on C with these marked points and orders of poles. And really, I want to consider just what is somehow the top stratum of this, such a space of quadratic differentials. So before I can even speak of a quadratic differential, I have to put a complex structure on this. So my space of quadratic differentials will fiber over the moduli space of complex structures. And I will probably abuse notation and keep denoting the Riemann surface by C And then this P, given a complex structure on the marked surface, can then be interpreted as a divisor in the sort of natural way, these points and these multiplicities. So we define this space quad CP to be the open subset of the vector bundle, well, of the total space of the bundle, whose fiber are the sections of the second tensor power of the canonical bundle of this Riemann surface. So that's what I mean by a quadratic differential twisted by this divisor P. I bring over the moduli space of complex structures on this genus G surface with these n-mark points. And yeah, I want an open subset, and the condition is that the section here has, well, I want it to have, I want this quadratic differential to have simple zeros and poles of order precisely P, not less. This is really this top dimensional stratum of the stratification of this by the orders of the zeros and poles. So in other words, I need the section to have simple zeros which are disjoint from the marked points Pi. Right, okay. So to get to defining this category, I'm going to look at a foliation on C given by, on the surface C given by a choice of such a quadratic differential in this space. Namely, a quadratic differential, well, it actually determines a metric on C away from its zeros and poles, because it's just this tensor. So I can look at the foliation on C, which is given by geodesics of a certain phase. So to put that in other words, we're going to look at what I'm going to call horizontal trajectories. So a horizontal trajectory of a given U in this space is so I'm going to look at some real curves on the surface. Call those gamma, which are disjoint from the zeros and poles. Of the quadratic differential U. And moreover, along which the quadratic differential has a given phase. So for which, so by that I mean, well, I mean a quadratic differential is almost an ordinary abelian differential. If I allow myself to take a square root, then it is, but that's ambiguous up to the choice of sign. So given a quadratic differential, I can always look at an abelian differential, but it has this sign ambiguity. But I'm just going to ask for the condition that the tangent vector to this real curve pairs with this to be real. Right. So that's what I mean by a horizontal trajectory. And then I guess one of the insights of Giotto, Moore, and Knightsky into this was that the foliation of the surface C by these horizontal trajectories has a very special form. So let's so they will will impose the condition that I'll try and label the zeros and poles consistently. So I'll label zeros by crosses and poles by blobs. Then suppose a U in this space called CP has no horizontal trajectories which run between a 0 and a 0. Then all horizontal trajectories incident to a 0 are also incident to a pole. So that's to say, if I have any horizontal trajectory which at one end hits a 0, then at the other end it's guaranteed to hit a pole. And moreover, these trajectories divide C into cells of T types. I should probably draw them up here. So I'll draw them in a sort of distinguished chart along C in which all trajectories are actually horizontal, as their name suggests. So I can always choose locally such a local coordinate which maps the horizontal trajectories into things which are actually horizontal. And then the cells look like this. So there's either this sort of infinite horizontal strip where there's a pole at both ends, and you have these distinguished special trajectories between the 0 and the pole along the boundary. And the remaining trajectories look like this. This is called a horizontal strip. Or potentially you can have a half plane. So you can again have a pole at either end, but just one boundary component. Like that. And moreover, we can actually compute the number of these horizontal strips. And this is precisely the dimension, the complex dimension of this space, quad CP. Which, yeah, I guess for, oh yeah, perhaps.
Can you do an example with z squared or z times 1 + 1?
Yeah, okay, yeah, we can try and draw an example. So, yeah, I was going to draw a slightly different example, but yeah. No, it's okay. Yeah, so, yeah, well, yeah. So I guess I was going to draw, so I was going to take C to be the projective line, and P to be 8 times the point at infinity, so a pole of order 8 at infinity. So yeah, I suppose I can try and draw that. So I guess, yeah, there's probably a couple of remarks I should make. So, yeah, well, so I mean, the way this this thing gets proved is by trying to sort of leverage the sort of local structure of this foliation into this sort of global statement. So it's important to actually think about what the local structure of this foliation is at the critical points, so at the zeros of the poles. Right, so at a 0, the local structure is like this. So, I mean, you have the 0, you have a local coordinate which looks like that. And this has this sort of symmetry of order 3. If I rescale this by any cube root of unity, this local coordinates, I get the same thing back. So if you then go ahead and solve this differential equation, you find the local structure kind of looks like this. So this has this sort of trivalent structure. And then around a pole, it's well, it's slightly more complicated. If we take a pole of order 8, for example, then, well, again, you have this sort of symmetry. I mean, here, I guess you have a sort of 6-fold symmetry. But if you actually solve the equation, you find that there are infinitely many trajectories which enter a pole. And they do so along one of 6 asymptotic directions in this case. So, yeah, we can draw those in blue. So you have this sort of local trajectory structure. So everything which gets sufficiently near to a pole falls into the pole along a given number of asymptotic directions, essentially. Right, okay. So I guess with that in mind, perhaps we can draw this example. So there are kind of 6 asymptotic directions off at infinity to which these trajectories go. And draw those like this. And then each of these, so you can compute, I guess, fairly readily that there are 4 zeros of such a differential. And each of those has this sort of trivalent structure. And under the assumption that I've put in here that there are none of these horizontal trajectories, each of these trajectories must go to a pole. So, yeah, something that kind of looks like this. So, yeah. So that would be an example of these sort of special separating trajectories of this foliation in this case. And then the remaining trajectories. Let's draw those in blue. Just foliate the surface like that. So we have 3 horizontal strips. Oh. These 3. And then we have 1, 2, 3, 4, 5, 6 of these half planes off at infinity. Right, okay.
So what's this equality correspond to here?
Yeah, this is, so, well, I guess we have to compute the dimension of this space of quad CP. I guess we can do that. So how is this defined? It was defined as the open subset of this bundle. So this is the sum of the dimension of the moduli space of complex structures. And, well, we have to work out the dimension of that space of sections. I guess. Yeah, here's C is, yeah, okay. But I was just going to write down. So this is the answer in general. If you, essentially there's a, well, you have a Serre duality between H naught of C and KC squared and H1 of C and KC joule, which is the dimension of this. And then you just have to add on essentially the order, the degree of that divisor P. So here this works out to be, if we think about this, this is -6. So G is 0, we've got this -6. There's 1 marked point with a polar order 8. So this indeed works out to be 3. Yeah, so they're indeed the 3 regions that, yeah. Okay. Right, so I guess it's certainly about time I constructed this category. So I guess the first thing to note is that this, well, the structure of this foliation has this graph of these separating trajectories, these special trajectories, which are in white up on that top board. And that's, in fact, a bipartite graph. So each of those separating trajectories runs between a 0 and a pole. So if I consider the dual graph to that, then I get an oriented graph, or in other words, a quiver. So I guess I should really draw that up there. Yeah, so let's draw this. Actually draw that on there. So if I consider the dual graph to this white graph, and then restrict only to the faces, which are these horizontal strips, so these 3. Well, the dual graph looks like this, and there's an actual orientation. Well, I have a choice of orientation I can give. I'll choose it to make sure I always go clockwise around a 0. So we have a quiver like that. Right. So, yeah. So U, a U in quad CP, which satisfies the assumption of this theorem, which doesn't have any of these finite trajectories, defines a quiver. And in fact, a quiver with potential. So that's a pair Q and W. Q is just given by the dual graph to these separating trajectories. And W, what's called a potential, that's just a formal sum of cycles. And we have natural cycles. I mean, that example kind of isn't big enough to see cycles around a pole, but they can exist. So this is a formal sum. Of the cycles around 0 minus the cycles around a pole. Right. So all along I've been carrying this assumption that we didn't have any of these finite trajectories. And so you might ask, well, quite how restrictive an assumption that is. It turns out they can only occur in real codimension 1 in this space quad CP. So in fact, there are local coordinates on this space quad CP associated to any given such decomposition into horizontal strips and half planes. And we get them precisely by associating a number to each horizontal strip. There's precisely as many of them as the complex dimension of this space quad CP. Right. And we do so by looking at a natural number associated to each horizontal strip. So the horizontal strips look like this. And there's a natural complex number, namely this one. So if I choose a coordinate to put this at the origin, then I've got this position of this other 0. So let's call this W. So let's call W the span of the horizontal strip. And you see that these spans define local coordinates. Well, a system of local coordinates. Well, so there are two zeros associated to each of these horizontal strips. So there's no horizontal what I've drawn here is precisely the horizontal foliation of the metric specified by this quadratic differential. There's no horizontal geodesic running between a pair of zeros. The horizontal geodesics I've drawn, but nevertheless there is one like this. So I can always choose a local coordinate to put my horizontal strip into the complex plane, and I have the freedom to put this given 0 at 0 in that coordinate, and this other 0 will be somewhere. We call that number W. So, no, so, okay, so what we're doing, I guess we're choosing a coordinate Z on C. So I guess that's a map C to the complex numbers, in which the horizontal strip looks like this. So in which, well, I guess, yeah, U looks like, right. And then within this, I'm free to translate the coordinate Z, so I can arrange for one of the zeros to be at 0. And I'm in fact free to change the sign of Z, so I'm free to arrange for this W to actually belong to the upper half plane. I guess that's the number I'm after. Mm-hmm.
And if you've chosen the other 0 instead, then it's the same number.
Right. So yeah. So yeah. If you want this to be at 0, and then you arrange for this other 0 to be in the upper half plane, then you do indeed get the same number. Yeah. Anyway, so yeah, so we have this system of coordinates, and in fact, yeah. So I was saying that quadratic differentials with these trajectories occur in real codimension 1, and indeed they occur precisely when such a horizontal strip degenerates into just this line. That's precisely when one of these spans actually becomes a horizontal trajectory of the thing. So this was a real codimension 1 condition. So quadratic differentials U in this space with such trajectories occur in real codimension 1. And they occur precisely where such a horizontal strip collapses. Okay, so I guess the question would be, what happens to this, the topology of this graph of separating trajectories as I pass through this real codimension 1 locus? And in fact, what happens is that that this quiver with potential that I've associated to this diagram undergoes what's called a mutation. So there's some well-studied combinatorial rule according to which this quiver changes as I pass through one of these real codimension 1 loci. Right. Right. So to this Q and W, I now have to associate a category. So so I want this to be a 3-Calabi-Yau category. And the way in which this is done is by looking at some DG algebra associated to this quiver with potential. I think I won't actually define, but you can see some of its properties. So this is called the Ginzburg DG algebra. Of Q and W. So this has two properties, I guess, that we're interested in. It has this Calabi-3 property, and it contains a standard heart, which is the category of modules, finite dimensional modules over H0 of this DG algebra, which is perhaps something a bit more familiar. This is called this H0 is the Jacobian algebra. Right, and another important property of this category is that you can somehow categorify the mutation of this quiver with potential via tilting of this standard heart. So this is a result due to Keller and Yang. So they show that there are a pair of equivalences so the pair is given by this sign, and then K is a vertex of this quiver Q. Between this category DQW and the category of the mutated quiver at this vertex K. So I'll denote that KQW. And the important property is that these equivalences send the standard heart into a tilt of, well, yeah, the left or right tilt of the heart with respect to the simple object of the category associated to the vertex K. So I guess in particular, although it might appear that we do indeed get lots and lots of quivers with potential associated to these quadratic differentials, because as we move in this space, we will cross these loci, and the quiver with potential will change by a mutation. Nevertheless, the categories are all equivalent. So we have a category which is essentially associated to our starting data of C and P. Associated to right. And we can, moreover, there's an actual, so I guess, yeah, now we need to talk about, the aim was to interpret this, our space of quadratic differentials as a space of stability conditions of some category. This is now the right category. So there's, how are we going to construct a stability condition on it? Well, a stability condition, of course, is given by the data of a heart together with a central charge, so together with some function from the Grothendieck group of this heart, or indeed this category, to the complex numbers. So how are we going to achieve that? Well, how do we get such a function? Well, we have to each vertex of the quiver, So the vertices of the quiver give us simple objects of this category, so they give us a basis of this Grothendieck group. We have precisely such a number associated in the upper half plane, namely the span of this horizontal strip. Right. So I guess that is the result, which is due to Tom Bridgeland and Ivan Smith. So I say we're actually going to interpret this space of quadratic differentials as a space of stability conditions. That's not quite true, because it's very difficult to rule out some fairly exotic connected components of spaces of stability conditions. So we're really going to consider the connected component of the space of stability conditions. Let's call this star of this category BCP which actually, I'm going to specify this connected component by asking that they contain stability conditions supported on any of these canonical hearts associated to these quivers with potential. So that's in some sense the natural connected component of this space of stability conditions. And then the result due to Bridgeland and Smith is that there is a dense, there is an embedding of this space quad CP has the structure of a complex orbifold as its natural structure, because it comes naturally as this fiber bundle over the moduli space of complex structures. So it inherits an orbifold structure from this space quad CP to, well, not quite the distinguished connected component, but of this category DCP that I have to divide out by a natural action of it, a natural action, which is the action of an autoequivalence group of this category, namely those autoequivalences which actually preserve this connected component. Okay, so this interprets a space of quadratic differentials as a space of stability conditions on this category. And we can actually go a bit further. So it's an embedding. Its image is in fact a dense open subset And moreover, Bridgeland and Smith actually describe how to complete this space of quadratic differentials so that you in fact get the entirety of this space. So I guess that's kind of a remark that there is in some sense, a completion of by allowing simple poles at the MI at the points Pi where MI is at least 2. MI is equal to 2. So by adding a few lower dimensional strata of of the space of quadratic differentials, so allowing what were double poles to degenerate into simple poles, you actually get the entirety of this space of stability conditions here. Okay, and I guess, well, in a minute or so, I guess I also said that you could interpret the stable objects through this equivalence. So, well, what indeed are the stable objects? Well, if you consider, let's just say this in words, so if you consider altering the definition of the horizontal trajectory to allow an arbitrary phase, then the stable objects are in bijection with trajectories of arbitrary phase of the given quadratic differential, which run between a pair of zeros. So those for the simple objects you can kind of see already as the spans of the horizontal strips, but as you alter this phase theta, you see the entire spectrum, as it were, of stable objects. Okay, so I should stop there. Thanks very much for listening.
So, at one point you seem to suggest that it was a case of trying to rule out these other components. I mean, I think it's fairly clear that there are stability conditions that aren't contained in this component, isn't it?
I wouldn't know how to construct such a thing.
Consider the derived category of the half. Okay, that's not true. But
yeah, it's tempting to say that I'm kind of obviously missing out hearts because all the hearts are like, yeah, they have finitely many simple objects or something like that. But
well, maybe we can talk about it.
yeah, sure.
So is every wall crossing in this stability manifold given by some mutation of the quiver?
Yeah, so yeah, I guess that was slightly brushed under the carpet. So I kind of gave the impression that you can actually pass anywhere within this space through these walls where the quiver actually undergoes this mutation. That's not quite true. So they're in fact, well, this is again an insight of the physicist Jotimur Naitsky, that there are 3 such these codimension 1 loci where these special trajectories can appear are in fact classified into 3, and they give them the names flips, pops, and juggles. So a flip is kind of what we've already seen. So they gave it the name flip because there's an actual associated triangulation as well here. because of the, essentially because of the trivalencies of this 0. So you can triangulate the surface, and the corresponding jump in the triangulation is what's known as a flip. There's a sort of less serious issue of a pop, which is kind of to do with possible degenerate horizontal strips. So in fact, it's impossible to rule out that in a horizontal strip, in fact, these two zeros might actually coincide on the surface. So you might have cells which have this sort of slightly bizarre looking topology like this. That's also a horizontal strip. So there's some, but that's really a sort of more of a technicality. And then the more serious issue is juggles. So it might not be clear that you can actually, it might be possible that as you do these flips and pops, these walls begin to accumulate. So you might, in principle, it might be possible that as you you pass from one, if you like, chamber of this space of quadratic differentials to the next through one of these codimension 1 loci, that these actually get closer and closer together, and you might never actually explore the whole manifold. And indeed, there are some places where these walls accumulate. They're called these juggles. But you can actually show, or Bridgeland and Smith show via some quite long computation, that in fact the juggles do not disconnect this space. So you can actually always go around them, and they're not really the issue that they might seem.